While everyone was watching OpenAI and the Stargate project, Mark Zuckerberg just quietly moved $135 billion onto the table. This isn't just a purchase, it's a total infrastructure hijack. Today, we're looking at the Vera Rubin platform, the secret NVIDIA superchip that Meta is buying by the millions to ensure no other company can ever catch up. If you think the AI race is over, you're looking at the wrong map. As these metrics glide across the UI, remember what matters: power, silicon, and orchestration. Meta stacks Rubin clusters pod by pod, squeezing efficiency point by point. The race isn't over, it's resetting right now. But here is the part that Bloomberg isn't telling you. The story isn't just about buying more chips, it's about rewriting the rules of computational physics. Meta isn't just buying chips, they are building hyper-densified data centers in Ohio and Louisiana that use more power than 750,000 homes combined. This isn't an upgrade, it's a ground-up reinvention of the data center, designed for a single purpose, to house the most power-hungry AI hardware ever conceived. Inside these racks, thick copper busbars move megawatts with minimal loss, feeding NVIDIA Rubin clusters that gulp electricity like small towns. This is industrial-scale power delivery, engineered for relentless, round-the-clock AI training, where even a fraction of a percent in efficiency translates to millions of dollars. Data ripples here are bandwidth in motion, terabits per second, crossing fabrics that stitch thousands of GPUs into one cohesive supercomputer. In this world, latency kills scaling. A microsecond delay can cascade into a failed training run. Rubin's interconnect keeps tokens flowing without choking the pipeline. Those light trails represent NVLink lanes, the neural pathways of the machine. Multiple hops bind trays into pods, and pods into clusters. The result, model shards, pieces of the AI's brain, communicate fast enough that compute, not the network, remains the bottleneck. This is the holy grail of distributed computing. Cooling is the quiet hero in this thermal battle. Chilled manifolds pull waste heat straight off the silicon cold plates, holding the chips at optimal envelopes. Higher sustained clocks mean more tokens trained per dollar, hour after hour, without thermal throttling. What looks like abstract UI is actually live telemetry: temperatures, pressures, error budgets, and power draw from every node. Meta's engineers tune these parameters in real time, squeezing every last percent of efficiency from every single rack. Behind each faceplate, backplanes route power and data with brutal simplicity. Shorter runs, thicker copper, fewer connectors. Every centimeter saved reduces electrical resistance and signal loss, keeping the entire Rubin fleet fed and stable. But why this obsessive focus on power and cooling? Because the Vera Rubin chips require a specific type of direct liquid cooling that Meta just patented. This isn't just about being efficient. It's a fundamental requirement to even turn the chips on. If you leave now, you'll miss the specific location of these sites and why they are being built near the US energy grid's dead zones, a strategic decision that changes everything. In the race for AI dominance, some moves are public, but the most decisive ones are made in secret. Jensen Huang and Mark Zuckerberg have one such pact, a strategic alliance that redefines the landscape. While other companies scramble for access to NVIDIA's Blackwell chips, Meta has leapfrogged the entire market. They've secured a multi-year, multi-generational deal not just for Blackwell, but for its successor, the Rubin GPU. This isn't just a purchase order, it's a partnership. This exclusive access creates an almost insurmountable supply chain moat. It's a strategic checkmate before the game has even begun for many competitors. For the foreseeable future, it doesn't matter how much capital rivals raise. Even if you have the money, you can't buy the most advanced chips, because Meta has already reserved the factory's output for the next 36 months. They aren't just buying GPUs, they're buying time and a guaranteed technological edge. At the heart of this advantage is the hardware itself. Rubin's backplane is an engineering marvel, routing terabytes of data with loss-tolerant links. Onboard diagnostics constantly verify path integrity as computational loads ramp, ensuring the uninterrupted flow of training tokens. Inside these data centers, airflow and service cadence rule the aisles. The environment is quiet, meticulously controlled, and optimized for continuous access without ever disrupting active workloads. This is a factory for intelligence, and downtime is the enemy. Cooling is an art form here. Microfans are merely for assistance. The real work is done by direct-to-chip cold plates and precisely balanced manifolds that pull heat away at its source. This aggressive thermal management allows for sustained, higher clock speeds. The coolant chemistry is a proprietary formula, tuned for near-zero electrical conductivity, microbubble suppression, and cavitation avoidance. Every variable is controlled to maximize long-term reliability, under punishing 24/7 operation. Power traces are interwoven with a mesh of telemetry sensors. This allows the system to predict and preemptively throttle performance just before thermal or power rail limits are breached, maximizing output without risking a catastrophic failure. The business impact is profound: higher sustained utilization. This translates directly to more tokens processed per watt and per dollar, hour after hour, day after day. It's a compounding advantage in efficiency that competitors simply cannot match. Massive copper busbars carry megawatt-scale power rails directly to the racks. The runs are kept incredibly short to cut resistive power loss, minimizing voltage droop even during the most intense computational bursts. Every component is designed for maximum uptime. Custom valves and quick connects enable hot swapping of entire GPU trays without draining the cooling loops or halting the system. In this high-stakes game, uptime is the only KPI that truly matters. These UI panels are not just displays. They are a live mirror of the entire operation, monitoring job checkpointing, shard health, and queue depth across thousands of Rubin pods at planetary scale. From the outside, it's just another anonymous building. But inside, it's a single monolithic computer, a brain stitched together from thousands of perfectly synchronized GPUs, all working in concert. This scale unlocks compounding returns. Yield improvements from the foundry mean better silicon bins, tighter clock tolerances, and lower variance across trays. This drives predictable, repeatable throughput, turning AI training from a science experiment into a reliable industrial process. Human intervention is the bottleneck. Technicians adhere to strict no-touch windows during peak training runs. The orchestration software handles everything else, eliminating human latency from the equation. The entire cluster communicates its status visually. The cadence of LEDs maps the cluster's state, pulsing green for healthy shards, amber for automated resharding and rebuild workflows. It's a living, breathing organism. Even the boot sequence is a synchronized ballet. Boot cascades push firmware, drivers, and network configs in perfect harmony, allowing hundreds of nodes to join the fabric simultaneously, without causing crippling packet storms. The air itself is part of the machine. What looks like haze is a visualization of airflow, managed by pressure differentials that keep harmful particulates out, while smart filters self-monitor their own lifespan. Faceplate indicators provide an at-a-glance confirmation of system health, showing stable power rails and ample thermal headroom, giving operators the confidence to push the system through marathon training runs that last for weeks. Data ribbons visualize the complex routing of mixture of experts models. Specialized expert circuits activate only when needed, a sophisticated technique to slash the immense compute cost of training and inference. Nothing is left to chance. Condensation control is fully automated, as even a single drop of water in the wrong place could be catastrophic. Every connector is pressure tested across extreme temperature swings to guarantee integrity. At this scale, even the weather matters. The system constantly analyzes external conditions, using ambient temperature and real-time energy prices to decide when to sprint on critical workloads or idle to conserve resources. A green status light signifies more than just on. It means the entire system is in balance. Tokens per second are steady, data retries are trending down, and overall utilization is holding near its theoretical peak. This phase of the war is defined by a simple truth. Compute is scarce. The winners will not be chosen by algorithms alone, but by the mastery of orchestration, power, and supply chain discipline. Next, we examine the staggering costs and the true scale of this ambition. By 2028, Meta will have spent more on AI than the GDP of Sweden or Argentina. This is the vantage point for today. The AI war isn't won by the smartest model, it's won by the operator with the most power and the most silicon. Meta just became that operator. This level of investment isn't just about buying more chips, it's about mastering the physics of computation at an unprecedented scale. Every component in this system is a deliberate choice, a calculated move in a high-stakes game of physical limits. Take the power delivery. Thick copper busbars tie NV-link domains, reducing impedance and crosstalk at brutal currents that would vaporize lesser conductors. The interconnect geometry itself is a weapon. By shortening signal paths and minimizing hops between GPUs, latency is crushed, unlocking more usable flops per watt. Pretty light, serious design, every detail, from maintenance ergonomics to safe service lanes, is engineered to preserve uptime and protect the investment. Frost is a controlled variable. Dew point automation prevents condensation during high load ramps, protecting sensitive electronics from moisture. This is direct-to-chip liquid cooling, the only viable path for this thermal density. Meticulous harness routing reduces electromagnetic interference. Clearly labeled looms and robust strain relief stop the simple human factor failures that can cripple a multi-million-dollar asset. Tray density climbs while service stays toolless. This focus on serviceability means mean time to repair holds the line, keeping the fleet available and the SLA intact. The LED choreographies aren't for show. They mirror workload phases: compile, warm up, steady state, checkpoint, giving technicians instant visual diagnostics. Power pins are over-specced with gold plating to survive thousands of mating cycles without arcing or fretting, ensuring a reliable connection every time. Cascading indicators mark shard rollouts. The system is deploying model updates with zero downtime, a critical capability for continuous operation. Lab sparks show rigorous testing. In production, every path is surge-tamed with redundant interlocks and constant monitoring to prevent catastrophic failure. Stainless steel manifolds prevent corrosion from the specialized coolant. Double-seal quick connects ensure leak-free swaps, even under pressure. Silhouetted racks show horizontal scale. Capacity expands pod by pod with predictable wiring and power draw, making growth a repeatable, industrialized process. Rubin racks hum along. Sophisticated orchestration software keeps the GPUs fed with data, pushing utilization above 90%, minimizing idle silicon. Glass reflections reveal isolation booths. The noisiest gear is quarantined to stabilize the acoustic environment, which aids both human operators and sensitive monitoring equipment. Cold plate flow holds the delta T, the temperature difference, inside a narrow specification, even under synthetic stress spikes designed to break the system. Sight glass bubbles confirm the system is degassing. Pumps automatically bleed air from the lines before any training jobs are admitted to the cluster. Outside, megawatts of power and open sky. Inside, trillions of tokens per second. This is where raw energy becomes the currency of language and intelligence. Those valve clicks are pure automation. Programmable logic controllers choreograph the cooling loops while technicians audit from a central console. Trace waves signify data locality. The architecture is designed to move compute to the data, not the other way around, saving precious time and power. Fleet telemetry from millions of sensors rolls up to a single SRE console, with strict red lines that trigger automated responses to anomalies. Thermal maps guide preemptive component swaps long before hotspots can degrade reliability or cause a cascading failure. Slow pan, fast scale. This infrastructure allows capacity to expand faster than rivals can even procure the necessary hardware. Microstructure advances in the backplane materials lift endurance, meaning fewer RMAs, less maintenance, and higher fleet uptime over the system's lifespan. This is the final bridge. Meta commits $600 billion not just to participate, but to own the curve, to achieve undeniable operator supremacy.